You know that feeling when you're in an exam, you flip the page, and you're hit with a massive question? Where do you even start? Well, today we're going to take on a full 12-mark GCSE Physics beast. And we're not just going to answer it, we're going to deconstruct it using the official mark scheme so you can see exactly what the examiners are looking for to award every single point. Okay, let's dive right in. Now, this question is pretty clever because it sneakily tests you on three totally different areas of physics. We're talking electromagnetic waves, a practical investigation on thermal radiation, and then it throws in some atmospheric physics for good measure. Let's break it down together. So we're going to follow the questions step by step. First, we'll hit the EM waves and X-rays. Then we'll get into that infrared investigation. After that, we'll tackle albedo and the atmosphere. And finally, we'll pull it all together and look at the big takeaways from the mark scheme that you can use on pretty much any exam question. Right, part one. This gets us warmed up with a classic test of your knowledge of the electromagnetic spectrum. Let's see what they're asking. So we're shown the EM spectrum, right? There's an arrow pointing all the way from the long wavelength radio waves over to the super high energy gamma rays. It's a multiple choice question asking what changes as you move along that arrow. This is pure recall, a straightforward test of what you remember. And here's the one-mark answer according to the mark scheme. The frequency increases and the wave speed in air stays the same. This is such a crucial fact. As you go toward gamma rays, the frequency shoots up, but the speed of all these waves in air is the same. It's the speed of light. That's the little trap they set in the question. Okay, next up is a two-marker. This one's about a real-world use, medical X-rays. Now, see that keyword, explain? That's your signal that you can't just state a fact. You have to connect a property of X-rays directly to how they actually let us see our bones. To grab both marks, the mark scheme is crystal clear. It wants two specific points. Point number one, you have to say that X-rays get absorbed by dense stuff, like bone. And point number two, you have to say that X-rays are transmitted or just pass right through the less dense stuff, like your soft tissue. It's that difference, what gets stopped versus what goes through, that creates the image. All right, switching gears completely now. We're leaving the theory behind and jumping into a practical investigation all about infrared radiation. This next chunk of the question is about experimental method, fair testing, and looking at data. So here's the setup they give us. You've got a kettle to make hot water, a special hollow cube with 4 different surfaces, matte black, matte white, shiny black, and shiny silver, and an infrared detector to measure the radiation coming off each side. First question in this section is a nice, simple one-mark safety check. The hazard is boiling water. All you have to do is suggest one common-sense way to lower the risk. And this is a perfect example of why the mark scheme is so helpful. It shows you they're flexible. You get the mark for almost any sensible answer. Handle it with care, use a lid, don't overfill it, put it on a stand. They're just making sure you have some basic lab safety awareness. Here we go, another one marker on the experiment. This time, they want a control variable. Basically, to make this a fair test, what is one thing you have to keep exactly the same every single time you take a reading? And once again, the mark scheme gives you options. You could say the distance between the cube and the detector, or the starting temperature of the water, or even the volume of water you use. Any one of those is a winner, because they all make sure the only thing you're changing on purpose is the surface of the cube. Okay, this one's a little trickier. They show you a table with only one reading for each of the 4 surfaces. Then they ask why you can't use this data to say if the detector is precise. This question is all about knowing what that specific scientific word really means. And the answer for 1 mark is so simple you might miss it. All you need to say is, the readings have not been repeated. That's it. Precision is all about how close your repeated measurements are to each other. If you've only taken one measurement, you've got nothing to compare it to, so you can't say a thing about precision. This is the last question on the experiment, and it's worth 2 marks. It gives you a student's conclusion and then asks a really interesting what-if question. What if they had used a less sensitive tool, a detector with a resolution of only 1 degree Celsius? How would that change things? And this lays out the problem perfectly. With the original sensitive detector, matte white was 65.5 and shiny black was 66.3 degrees. But with a detector that only reads to the nearest degree, that 65.5 would round up to 66 and the 66.3 would round down to 66. Suddenly, it looks like a white surface and a black surface are giving the exact same reading. This makes the student's conclusion that black surfaces always emit more, well, invalid. If you explain that rounding issue and the impact, you get both marks. And we're on to the final part with another big topic shift. Now we're diving into atmospheric physics, and this idea you might not have heard of before, called albedo. Now, this is a pretty kind question because the paper actually tells you what albedo is. It says a value of 1.0 means perfect reflection and 0.0 means perfect absorption. So albedo is just a fancy number for how reflective something is. The question then simply asks, what's the albedo of a perfect black body? Well, by definition, a perfect black body is a perfect absorber. It soaks up all the radiation that hits it and reflects absolutely none. So, using the scale they literally just gave us, its albedo value has to be 0.0, a nice, easy mark for just reading carefully. And here it is, the final question. And it's a big 3 marker. We see 2 points on the ground at night. Point A has a clear sky above it, but point B is tucked under a cloud. The question is, why does the air at point A with the clear sky cool down faster? To get all 3 marks here, the mark scheme wants a clear, logical story in 3 parts. Mark 1, you have to state that the Earth itself is radiating heat out into space. Mark 2, you have to explain that the cloud over point B acts like a blanket, reflecting or radiating some of that energy back down. And Mark 3, you bring it home by concluding that because of this, there's less of a net or resultant energy loss at point B, which is why it stays warmer. And that's it. We have totally picked apart that 12-mark question. We've seen it all: multiple choice, safety, data analysis, long explanations. So what's the big lesson here from using the mark scheme as our roadmap? The single biggest secret the mark scheme tells us is this: getting full marks is not just about knowing the physics. It's about communicating that knowledge with precision. It's about using those exact keywords: control variable, resolution, transmitted. It's about seeing a 3-mark question and knowing you need to make 3 distinct logical points. That's the real game changer for acing your exams, learning to think like the person who's going to be marking it. So just think, what other subjects could this approach work for?